Welcome to DataMites family. In today's video, we'll be seeing about a very famous time series forecasting model called as ARIMA. So what is ARIMA? ARIMA stands for Auto-Regressive Integrated Moving Average. It is a statistical model that forecasts future values in a time series based on past values. So it finds its importance in finance, economics, and other fields, wherever the prediction plays a crucial role. So it was developed in 1970 by Box and Jenkins as an extension of ARMA. The key features being it handles non-stationarity in the time series data, captures patterns and trends in the data, and provides a framework for model selection and evaluation. So the components being AR autoregressive uses past values to forecast future values. We have seen this in the definition. So example being, it is the most famous project you must have already worked on as the stock price prediction project. So the stock price today is influenced by its price yesterday and the day before it. Integrated. Here, the integrated stands for accounts for the non-stationarity in time series. Differencing is used to make the time series stationary. So the most key word here is we have to make this data stationary. That is when this ARIMA model can be built. Example, a time series with a strong trend can be made stationary by taking the first difference. Moving average, it uses errors from past predictions and forecast future values. We call this use errors as residuals. The errors are referred to as residuals. It captures the random fluctuations in the data. And stock price today's prediction is influenced by error in predicting its price yesterday. So this is the components, the terminologies, and the formula. So in ARIMA, I have in the parameters P, D, and Q. So P stands for number of autoregressive terms, D stands for degree of differencing, Q stands for number of moving average terms. So this is the formula. And these are the terminologies. Here x underscore t is the time series value at time t. C is the constant. Plus pi underscore I here we have provided are the autoregressive coefficients. All this along with the pi are referred to as autoregressive coefficients. And along with theta, if you find it, they are moving average coefficients. And you can also see terminologies like E underscore T. They are the error terms at time T. So the autoregressive terms captures the patterns and trends, and moving average captures random fluctuations in the data, and the constant term captures the overall level of time series. So the model is estimated by the maximum likelihood estimation. So what is MLE? Maximum likelihood estimation stands for. It finds the parameters that maximizes the likelihood of the data. So there are other methods of estimation as well, which are least used. Coming to the validation, check for model assumption, whatever the stationarity, normality, and homoscedasticity. These are the basic key things we have to check for. That the time series which you are working on, it should be stationary, and the errors of the residuals should be normally distributed, and the residuals should have a constant variance. And with these residuals or errors, we have to go for pattern and trend in the residuals. And also check for the outliers and anomalies. Out of the sample, forecasting performance. So evaluate the model performance on a holdout data set and compare its model's performance to benchmark and other models. So these are the methods to check for stationarity. ACF, autocorrelation function, partial autocorrelation function, AIC, BIC. This will suggest us to go ahead with what parameters and check for the stationarity. So plots the correlation between the time series and its lagged values, the ACF. PACF is similar, but it plots the correlation between time series and its lagged values, controlling for the effects of intermediate lags. And AIC BIC measures the relative quality of the model. So the applications of ARIMA is in finance industries, like stock price predictions, exchange rates, commodity prices, and in economics for GDP, inflation rate, unemployment rate, and in other fields like weather forecasting as well. What is the limitation of this ARIMA? First is that it assumes linearity. It assumes the relationship between the time series and its past values is linear, which is not the actual case. And assumes normality. Whatever the residuals present, they are normally distributed, it assumes, which is again unlikely case. The third is it assumes the time series is stationary. Most of the times, the data which we get, they are not stationary, non-stationary ones. So we have to convert it into a stationary data. And it does not handle seasonality. To overcome this limitation of seasonality, we have a separate model called as SARIMA or seasonal ARIMA. And there are other similar models called ARIMAX and SARIMAX. And whenever you find a non-linear relationship, it fails to give you the accurate predictions. So as I've spoken, ARIMA has even the extension called SARIMA. Here, the seasonal aspect is taken care of. And the other extensions being Varima, Vector Arima. Varima is also called as Vector Arima and ETS. These are the other extensions of Arima. So Arima is a powerful model of time series forecasting, but it has its limitation as we have seen. And there are extensions as well, like Arima, Sarima, ETS, Varima, and all, where there is scope of improvement as well. And these can handle more complex time series data. And the ARIMA should be used in conjugation with other models and technique to ensure accurate and reliable forecasting. Let's see the code aspect of it. So in the code aspect, here you can see there is list 1, list 2, empty list. And there are params. In the params, I have given all the combinations. 0, 0, 0. For the P, D, Q, I have passed on different combinations starting from 0, 0, 0, 0, 0, 1 and so on until 999 pops up. That is a last probable combination. So it will go ahead and try with all the combinations as seen here. The ARIMA, we fit the training data set. And what is the order? The params. Params is a loop. And we also check for the AIC. Again, we need a least value of the AIC to tell our model is performing good. And later, whatever the parameters are there, I appended it to the list 1. And whichever is having the least, I try to append it to the list 2. So these are the combinations which you can see, and it is calculating the respective AIC for that particular combination as well. So in the list 2, we have the AIC. So as I've told you, we want the minimum AIC out of this entire combination. So out of this entire combinations, what we are searching is for the minimum AIC score or the lowest AIC score in the above combinations. And there is a 16 score. Where is it? The location is 575th location. You are getting the minimum. What is that particular combination? So it is having P, D, Q of combination of 5, 9, 2. So in orders, we have to pass this particular combination to get the best score. So again, I take the ARIMA with the training and I give an order of PDQ as fine 9 and 2. And I fit the model and I see for the AIC again, just to be sure, confirming the AIC, yes, it is 16. Further, I go ahead and forecast it to the next 42 steps. So you can see here, these are our prediction. So thank you for watching the video. We'll meet again in the next video.